All right. So next up, we're going to talk about magnets and wires. There's two different ways that we're going to look at this. One is the effect of a magnet on a wire that is carrying electricity. And the second is the magnetic field created by a wire that's carrying electricity. So when we talked about the force on moving charges, we had F equals Q V B sine theta. Okay, and V is actually is distance over time, right? Okay. If we want for a wire, what we want to do is we want to take advantage of the fact that we know what Q over T is. Q is charge per unit time, Q over T is, and that is equal to current. The distance in the case of a wire application would be length, and then B sine theta. So the length of the wire in meters, the current in amps, and B in Tesla, which is capital T. Okay, so it's the same but rearranged. So instead of having QV, we have IL, and it just the only difference is the time is what the time is underneath of in the fraction. Okay, now where does that point? Well, it points in the same way that it does with the right hand rule. So in the right hand rule, if I have a B field, and I have a velocity, that looks like here, a velocity, right? Using the right hand rule, my force would be into the plane, right? Pushing that way. But charges can also move inside a wire, and when it's moving inside of a wire, it's called current. Okay? Current going through a wire feels the same force that it would if I was looking at it one charge at a time. And so you still use the right hand rule, but you replace V with current. And this V that I'm talking about here is not voltage V, it's velocity with current. Okay, so same idea. Now, why? What does that matter? Well, if, for example, if I start a high voltage current that's connected through a high power line, when I flip the switch, I can actually see that that wire start to oscillate. Why? Because there are magnetic field lines that are passing through, and if I have, so for example, I've got power lines and I have a wire and I have current going in this direction. if the magnetic field at this location is pointed toward the north, I'm sorry, from, let's see, toward the north geographic, which is south magnetic, what happens is that the magnetic field and the current determine that there is an upward force on the wire that starts when you start running the current through the wire. When I turn it off, it'll sag down again. And so I can see the effects of it very specifically. Two related things that I want to mention that I didn't the first pass through. There are other magnetic strength units, and that is Gauss, which is a capital G, and one Gauss is equal to 1 times 10 to the minus 4 Tesla. Okay? All right. The other thing I wanted to mention is in relation to the compass. And when we talked about using the compass, right, we said that the Earth acted as if it had a south pole at the north geographic pole and a north pole at the south, right? Right. That's going to create magnetic field lines that wrap around the Earth, and those field lines always point south, right? So as we go from north to south, the magnetic field lines point in toward south. They come out of the north. Okay. And we can use our compass, especially at far north latitudes, to tell relatively how far we are from the North Pole. Here at central latitudes, if I hold the compass in my hand, it points pretty much horizontally toward the North Geographic Pole. As I get closer and closer to the North Pole, if I were to hold my compass in a vertical orientation, what I would see is that the compass would actually point downward because the magnetic field points more and more steeply downward as you go toward the north. So not only can I get like the North Pole is that way, I can also get a sense of how close it is by turning my compass on its side. And if I'm far from the North Pole, it's horizontal. The closer and closer and closer I get to the North Pole, the more vertical it gets. At the North Pole, it would stand completely on its end. So, something I didn't mention on the way through. All right. So, the other thing we want to talk about with magnets and wires is if I have a wire with a current that is traveling in this direction, current in a wire creates a magnetic field around it. Okay, and we use our right hand again in a different version of the right hand rule. And what we're going to do is align your thumb with the current just like you would normally, but then the natural curve of your fingers, right? If I were to grab this wire with my right hand, my thumb pointed in the direction of the current. My fingers show me the direction of the magnetic field. Grabbing the wire, my fingers go in, around the back, and out the front. So I create a circular magnetic field, which if I looked at the top view, where here's my wire and my current is coming out the top, right? Coming out the top. If I turn that toward myself, I see that my magnetic field wraps around in a counterclockwise direction. And there will be lines of magnetic field that extend outward, and they'll get fainter and fainter and fainter as I get farther and farther and farther away. But my magnetic field is going to wrap around my wire according to the right hand rule. Thumb the direction of the eye, fingers the direction of the magnetic field. Okay? Now that becomes important if we talk about a loop of wire. If I take a loop that, let's see, let me get a visual aid. Okay, here's a loop, okay? If I take wire in a loop and I want to draw it so that it's kind of at an angle, so it looks narrow, but it's actually a circle viewed from the edge on, okay? So if I have current entering here, going around the backside, across the top side, and down the other side, all right? That's going to create a magnetic field according to my right hand rule. And so with the right hand rule, if I grab, let's see, which way did I put it? I put the, ooh, that's not happy. All right, I'm going to do it from this way because I want my thumb to be pointed the direction of the back side of the loop. My thumb is pointed up. My fingers wrap around and into the loop. Okay, so that means that the B field comes around the back way. When the current is going up, on the side of the loop, which is the front side, where the current is pointing down, so this loop again, on the front side, where my current is pointing down, my fingers wrap into the loop as well. Really awful image. But what you'll get is you're going to get, if I do it completely flat from the side, let's see, how do we do it? Current up, yep. On the back side, we've got a magnetic field that wraps around that looks like this, right? Around this way for the top of the circle, and around the bottom of the circle, around that way. That is just like having a bar magnet that has current going in at the south and out at the north. So a current loop creates a magnetic field that's aligned through its middle. And we'll pick up from there.